going to talk about solutions, which is a homogeneous mixture. And in a solution, there are two parts. There's what we call the solvent and the solute. The solvent is going to be your larger part of the solution. It's going to have a larger amount. Your solute is going to be the smaller part. Sometimes the solvent is also called the dissolving medium. Whenever you dissolve a solute in a solvent, it makes a solution. It's homogeneous. It's uniform throughout. The particles will spread out evenly within the container, but you can't see them. Water is our most common solvent that we deal with in chemistry. And whenever we dissolve a solute in water, we refer to it as an aqueous solution. We've already talked about how water is a polar molecule. It has a bent molecular geometry, which makes it be asymmetrical and polar. And when that happens, because of the polar bonds, the hydrogen becomes partially positive and the oxygen becomes partially negative. This is what lets water be really good at dissolving ionic compounds. So this picture on the bottom shows what's happening. So if I dissolve sodium chloride, the sodium separates out from the chlorine. The sodium is your positive ion, the chlorine is your negative ion. And then the water is attracted to the charges of those ions. And so sodium is a positive ion, so the oxygen end of the water, which is a partial negative, is going to be attracted to the sodium. And then on the chlorine ion, which is a negative ion, the hydrogens, which are partially positive, are attracted to the chlorine. This is called hydration. Whenever you dissolve a salt in water and the salt falls apart or dissolves and the water is attracted to the separate ions. When you have an ionic substance, we just call them salts. They're always going to break into your individual ions, your cation and your anion. Your cation is always going to be attracted to the oxygen end. Your anion is always going to be attracted to your hydrogen end. The solubility of a substance depends on several factors. One of the biggest ones is going to be attraction of the ions, so the attractive force between the positive and negative. And then it should say the attraction of the ions, not tions, to the water molecules. And so when that happens, the opposite charges are going to be attracted to those partial charges on the water. Some molecular substances can also dissolve in water. So remember, molecular means that it's covalently bonded, but some of them can dissolve in water because they do have a hydrogen bond. And so because they're similar to the water with the hydrogen bond, they're able to dissolve into each other. Nonpolar substances do not dissolve in water. So like fat is an example of a nonpolar substance. And so if you pour oil in water, if you're cooking, if you're making a dressing, that oil does not dissolve because the oil is nonpolar and the water is polar. You have to have similar substances in order for them to dissolve into each other. So let's just talk about a little bit about how we determine how concentrated a solution is. And what we use for that is something called molarity. And with molarity, it's just a basic equation. Molarity is equal to moles of your solute divided by your liters of your solution. It's a pretty straightforward equation. And we use this equation a lot now, but we use it a ton when we get to the acid-base chapter. And so let's get comfortable with how to calculate these things out. In order to use the molarity equation, we have to have moles and liters. Well, in this problem, it says calculate the molarity of a solution prepared by dissolving 11.5 grams of solid NaOH in enough water to make 1.50 liters of solution. Well, we already have our liters. We do not have our moles, but we can do a basic gram to mole conversion. So I'm starting with, might help if I was on the pen. So I'm starting with 11.5 grams of NaOH. If I start with grams, I got to cancel with grams. This number comes from the periodic table. I have just written down 40, but let me figure out exactly what it is. So sodium is 22.99 plus oxygen, which is 16, plus hydrogen, which is 1.008, and that gives me 39.998. And grams is always equal to 1 mole. So then I'm going to do 11.5 divided by 39.998. And round it to 3 sig figs because of 11.5. It gives me 0.288. That's going to be my moles of NaOH, which is my solute in this problem. So then I'm going to solve for molarity. So I'm going to say molarity is equal to my number of moles, which is 0.288 moles. You do not have to write the substance down when you're doing the actual molarity. You do with the conversions. Divided by your liters of solution, so 1.50 liters. And so then you're going to divide that out. So 0.288 divided by 1.5 gives me 0.58. Hold on, that doesn't make sense. It can't be bigger than what it was. It's going to give you 0.192 because I still need 3 sig figs because of both of those. And technically the units are additive. It's moles over liters, but scientists shorten it to just a big M to represent molarity. Next one says calculate the molarity of a solution prepared by dissolving 1.56 grams of gaseous HCl in enough water to make a 26.8 milliliters of solution. So the problem with this one is I don't have anything in the right unit, so I got to convert everything to the right unit first. So I'm going to start by my gram to mole conversion, so 1.56 grams of HCl times, I'm going to do the mass of 1 hydrogen, which is 1.008, plus 1 chlorine, which is 35.45, and that gives me 36.458 grams of HCl to 1 mole of HCl. So then again, mathematically, I'm going to do 1.56, technically times 1 divided by 36.458. I need 3 sig figs. And this one comes out to 0.0423 or 428. And that's my moles of HCl. So then I'm solving for molarity. Now, this is in milliliters. I have to convert it to liters. I'm going to do 26.8 divided by 1,000. And I'm going to get 0.0268. That's a very common conversion we have to do in chemistry. Be sure that you're including those leading zeros and that you're not forgetting to write them in. That's a big mistake people make. So 0.0428 divided by 0.0268. I need 3 sig figs, so it's going to round up. It's 1.597, so it's going to round up to 1.60 molarity. So sometimes you're just going to be given grams and you have to convert to moles. Sometimes you might already be given moles, you just plug it in. And then a lot of times because in lab we measure in milliliters, but we have to convert it to liters for this equation. So a lot of times your problems are going to be given to you in milliliters, not liters. But sometimes we're lucky and it's already in liters. So this is something that we start into now and comes up a lot throughout the year. There's this concept called a dissolution equation. And in a dissolution equation, we're saying what would happen if I put this in water and it dissolved and broke into its ions. And then this problem is asking me, what's the concentration of each type of ion in the solution? So the first thing we got to do is the dissolution equation. So for a dissolution equation, you're going to take your given salt, which will be in a solid form. So this is a solid. And it's going to break down into its ions, which become aqueous. So if you don't know the charges of things, you can always work backwards from the other things. So the NO3 is a polyatomic ion. It has a charge of -1. If there's 2 of them, then the cobalt has a charge of +2. So I'm going to do cobalt +2. It's aqueous plus my NO3, but there are 2 of them because of the subscript. We have to keep true to the number of each substances in this. So it's going to be 2 NO3s -1, and this is also aqueous. In an AP exam, if you told the charges, you would get points. If you left out the charges, you would not get points because it wants to know that you understand it is an ion. So then we got to figure out the concentrations from this problem. So it tells me this is 0.50. And then what do we do from there? Well, it's all about molar ratios. So this is considered 1. That's considered 1. This one was 2. So 0.5 molarity of this is going to produce 0.5 molarity of cobalt, but it's going to double my nitrate because for every 1 cobalt nitrate, it is going to make 2 nitrates. And so you're going to do 0.5 times 2, which is going to give you 1. Let's do that again with the second equation. So the second one gives me FeClO4 3. Again, if you haven't memorized some of the polyatomic ions, you probably want to. It makes your life easier when we do these dissolution equations. ClO4 is perchlorate. It has a -1 charge. There are 3 of them, so iron is going to have a +3 charge. This is going to be Fe +3 aqueous plus ClO4. It is -1, and there are 3 of them in this problem. This is 1, this is 1. So then it tells me that this is 1 molar. So for every 1 molar of iron perchlorate is going to produce 1 molar of my iron ions, but it's going to produce 1 times 3, so it's going to produce 3 molar of my perchlorate ions. So it's just pretty straightforward. It is just a relationship based on the moles, and this is called a dissolution equation. I start with my solid, and I just break it down into its individual ions, showing the charges and the states of matter. Last practice problem for now is calculate the number of moles of chlorine ions in 1.75 liters of 1.75 liters of 1.0 times 10 to the -3rd molarity ZnCl2. So this gives me a lot of information. It's giving me a solute, but it's asking for an ion. So what we're going to have to do is we need to first start out with our dissolution equation. And so we're going to do ZnCl2 solid. It's going to break down to Zn. Chlorine is a -1, so that means zinc has to be a +2 because there are 2 chlorines. Also, if you would memorize that zinc is a +2 always, that's the only charge zinc can be. And then chlorine is a -1. And the AQ is just for aqueous, the S is for solid. And then I need to balance it. So this is going to be for every 1 of these. I'm going to produce 1 of those, but 2 of those because of that subscript. So first thing I need to do is figure out how many moles of my ZnCl2 is going to be produced. And that's where I'm going to use my molarity equation. I'm going to do 1.0 times 10 to the -3 molarity of my solute. Sorry, wrong symbol. Is equal to, I'm going to solve for moles. It tells me my volume is 1.75 liters. So then I can mathematically solve this out. So I'm going to do 1 times 10 to the -3rd times 1.75. And that comes out on my calculator to 0.00175. So then if I go back to this, then that means this is 0.00175 for it. That'd be 0.00175 for it. And then it'd be that times 2. So it'd be 0.00350 moles of this. Another way you could work this out if you just want to do a mole conversion like with stoichiometry. Again, I'm going to do 1 mole to 2 moles of chlorine. So every 1 mole of ZnCl2 in this equation, I'm going to produce 2 moles of chlorine ion. And that would also give me 0.00350. AP would accept either way if you use the equation and showed the relationship, or if you worked it out in a stoichiometry method. So we use the molarity equation in a lot of ways. It is a very common equation, and you need to get really comfy with using it, but also understanding how to convert to liters from milliliters and how to deal with these ions.